Last week, reports surfaced that Elon Musk is planning to construct the world's largest semiconductor fab to achieve total independence from foreign foundries. Entering this industry requires more than just capital. It requires mastering the staggering mechanical reality of extreme ultraviolet lithography, or EUV. EUV is the process of using short-wavelength light to etch billions of microscopic transistors onto a single chip, a process currently controlled by a single company in the Netherlands. The tech community was quick to point out the gaps in the plan. Critics cited impossible delivery dates, missing supply chains, and total lack of local expertise in a field where established giants struggle to keep pace with current manufacturing standards. Why would a CEO risk his reputation by announcing a project that seemingly ignores the physical constraints of the industry? If we look at this as a standard business expansion, the math simply doesn't add up. To understand the logic here, we have to look past the visible engineering goals. Every complex project operates on two levels, the stated objective and the hidden driver. Without a specific destination for the hardware being built, a project of this scale would just be an expensive distraction. The fab itself is the visible manifestation of a larger internal requirement for Musk's other ventures. Standard financial metrics fail to explain this move, because the factory isn't being built to compete for customers. It's being built to solve a specific biological bottleneck. The core of Musk's long-term strategy often centers on the vulnerability of the human body and the risk of biological extinction. Neuralink's immediate goal is medical, using high-bandwidth brain-machine interfaces to restore autonomy to patients with severe paralysis. The project also explores the long-term possibility of mapping the human connectome. The connectome is a comprehensive map of all neural connections in the brain, which could theoretically allow memories and personality to be stored as digital data. Preserving human consciousness in a digital format requires a level of data processing and real-time simulation that exceeds the capacity of every existing server farm on Earth. If the goal is to shift consciousness from biology to silicon, the availability of that silicon becomes a matter of survival. Owning the fab is the only way to ensure the hardware exists to host that data. This roadmap follows the Kardashev scale, a method proposed by Soviet astronomer Nikolai Kardashev to measure a civilization's advancement based on its energy consumption. This scale categorizes modern humanity as Type 0. We use significant energy, but have yet to fully harness the total resources of our own planet. A Type 1 civilization has mastered its planetary energy and integrated its biological intelligence with machines to manage those resources. Beyond that lies Type 2, a species that harnesses the total output of its home star. This often involves a Dyson sphere, a hypothetical shell of energy collectors built completely around a sun to capture its radiation. Musk's companies appear to treat these theoretical milestones as tangible engineering targets. The chip fab provides the computational foundation required for a species, attempting to outgrow its biological limits and transition to a planetary-scale intelligence. This strategy creates an interdependent ecosystem where every company serves as a specialized department within a single objective. SpaceX provides the physical transportation required for expansion beyond Earth. While SpaceX handles the transport, xAI develops the superintelligence, Neuralink provides the human interface, and the fab provides the hardware to power the entire system. The success of one company creates the necessary environment for the others to exist. Each entity solves a specific piece of a multiplanetary puzzle, creating a closed-loop system designed to sustain the species across different worlds. The transition from a Type 0 to a Type 1 civilization is considered the most volatile phase for any species. It is the moment when technological power often outpaces social and physical stability. But even the most expansive and ambitious plans must eventually collide with the hard laws of physics. Without specialized components from companies like ASML, the plan for a self-sufficient ecosystem remains stalled. Hardware limits cannot be solved by ambition alone. We are witnessing a high-stakes attempt to engineer the future of the species. Whether it succeeds depends entirely on whether the physical hardware can finally catch up to the scale of the vision.